Assalamu alaikum. So let's have a go at this October 2022 paper. Okay, question 1, which of the following is given by the area under a velocity time graph? Well, technically you should have memorized that this is just the displacement. But generally speaking, the area under any graph is going to be the y-axis, whatever's in the y-axis, multiplied by whatever is in the x-axis. For velocity time graph, it's going to be velocity multiplied by time. So velocity multiplied by time. We know that velocity is the change in displacement over the time. So change in displacement over time is the velocity multiplied by time. The times cancel out. You're just left with displacement. So you could use this to work out what the area under any graph represents, in case you've forgotten or in case you just, something new, a new sort of graph is given in a question. And also worth noting while we're here, that the gradient gives you the y-axis over the x-axis. So the gradient of this specific graph will be v over t instead of v multiplied by t, and v over t is velocity over time, which is acceleration. Which of the following quantities is a vector? Again, this is something you need to memorize. What are your vector and scalar quantities? And from the list, the only vector is momentum. The rest are all scalars. They do not have a direction. Which of the following best describes the situations in which Stokes' law applies for objects moving in a fluid? Option A, all spherical objects moving at low speeds. Well, it's not all spherical objects, because I'll give you a scenario of a spherical object that wouldn't obey Hooke's law. Let's say the spherical object is big enough that it's very close to the edges of the container. And you should know from flow, like laminar and turbulent flow, that something called streamlines. And you should know that the streamlines next to the surface always have the most friction of the surface. And this extra layer of friction might actually make the sphere not obey Hooke's law. And there's other examples of spheres not obeying Hooke's law. So just something you need to memorize, I guess. It's not all spheres, so it can't be A. Option B, all spherical objects. Well, again, not all spherical objects, so it can't be B. Option C, small spherical objects moving at low speeds. Well, that sounds like a very good option, but let's have a look at D in case it's better. These are small spherical objects in the fluid with low viscosity. Well, you should know that if you have a low viscosity, there's not going to be that much viscous drag, right? Because you should know that the viscous drag is proportional to viscosity. So the lower your viscosity, the lower the viscous drag. And if there's less viscous drag, then your spherical object is probably going to travel at high speeds. And you don't want high speeds for Stokes' law, because Stokes' law involves low speeds, spherical objects, and laminar flow. So C is the best option out of all of these. Question 4, a car accelerated along a straight road. The graph shows how the acceleration of the car varied with time. So what we could see is that this is a decreasing acceleration. And it's decreasing at a constant rate as well. So decreasing acceleration. And it's asking which of the following graphs shows how the velocity of the car varied with time. So how do I show decreasing? This is what I'm trying to do. How do I show decreasing acceleration in the velocity time graph? Well, the first thing you do is you draw your velocity time graph. And you should be thinking, well, what is acceleration in a velocity time graph? Well, the acceleration in a velocity time graph is the gradient, because we know velocity over time is acceleration. So I need to show a decreasing acceleration, i.e. I need to show a graph where the gradient is decreasing, because the gradient represents the acceleration. So any graph where the gradient is decreasing and decreasing and decreasing, i.e. it's like a curve, like a decreasing curve, is going to show you decreasing acceleration. And the clear option out of these four is A. A sample of a material is in the form of a wire. The material has a large value of the Young modulus. Which of the following statements best describes the material? It has a large Young's modulus, and we know Young's modulus is equal to stress over strain. So having a large Young's modulus will mean that your ratio of stress to strain, which is the definition of Young's modulus, is high. So which of the following four options tells me that the ratio of stress to strain is high? Well, let's look at A. A says a large force per unit cross-sectional area is required to break the wire. This is a force per cross-sectional area. So force over area. This is stress. So we're saying a large stress is required to break the wire. This is referring to the breaking stress. And actually, the breaking stress has nothing to do with Young's modulus, because you could have a material with a high Young's modulus, and the Young's modulus in a stress-strain graph is just a gradient, because stress over strain is Young's modulus. So I could have a high gradient, a high Young's modulus. So let me draw like a steep line, a high gradient, with a small breaking stress. So here's my breaking stress. Whereas I could have another wire, another material with a low Young's modulus, so a low gradient. So let's draw something less steep. However, the breaking stress is higher than the previous one. So this alone shows that the breaking stress has nothing to do with Young's modulus. So it's not A. B says the mass per unit volume. Well, what is mass per unit volume? So mass over volume, you should know, is density. And density is not really related to Young's modulus. Because if you look at the equation, is there any density involved? Is there any mass over volume involved? The answer is no. In fact, mass is not even part of Young's modulus, because this is force over area over, and this is the force you're applying, by the way, not the weight of the material. So force over area over stress over strain, which is extension over length. Nothing here has anything to do with mass, the mass of the wire. So it can't be part B or option B. Let's have a look at C. The ratio of tensile stress to tensile strain is large. Well, the ratio of stress to strain is large. Well, this stress over strain, this ratio is what Young's modulus is. So if this is large, Young's modulus has to also be large. So the answer is C. A rubber band is initially stretched by an increasing force. When the force is gradually decreased, the rubber band returns to its original length. The force extension graph for the rubber band is shown. P, Q, and R represent different areas of the graph. Which of the following gives the work done in stretching the rubber band up to its maximum extension? Well, the work done is the area under the graph. So if you have a force extension graph, the work done will be the area under the graph. And once the work done, i.e. the area under the graph in stretching. So the area under the graph in stretching. So let's have a look at us stretching it here. We want the area under this. So it's going to be all of this. So the area under is clearly Q plus R. Therefore, the work done is Q plus R. And just a reminder, the area under the graph is the y-axis multiplied by the x-axis. And in this case is force multiplied by extension. This is the same as force multiplied by displacement, which we know is work done. Work done is force times distance, right? Okay, so it will be Q plus R. That confused me for a second. All right, two forces X and Y at a point. Which of the following vector diagrams shows the magnitude and direction of the resultant of the two forces? Well, any two vectors that sum to give a resultant, when you're drawing and when you're illustrating it, you have to draw the vectors tip to tail. So that's the rule. These two vectors, X and Y, are drawn tail to tail. So it can't be A. For the same reason, it cannot be B. Okay, now C and D, both of these vectors X and Y are drawn the tip of one vector is touching the tail of the other. So it's between C and D. We should also know that the resultant force is in the direction from the start of your first force towards the end of your second. So from the tail of your first vector going towards the tip of your final vector. So the answer will be C. As you can see, D is going in the opposite direction. It's like you started here, you ended here. You know, how can the resultant be in the opposite direction? Okay. When a certain spring is stretched by a tensile force F, the elastic energy stored in the spring is E. So let's draw this. So let's say we have a certain spring and you're applying a force F and it's stretched. So let's say it's stretched by some extension delta X. The elastic energy stored in this case is E. So there's the energy of, let's say the elastic strain energy stored in this spring is E. And we know that E is equal to the elastic strain energy stored in the material is equal to half the force applied multiplied by the extension. So this is the elastic strain energy stored in this one spring. Now we're saying 3 of these springs, the same spring, 3 of them are arranged in parallel and stretched by a force of 2F as shown. Which of the following gives the elastic energy stored in the parallel system? And as you could see, all options are in terms of your first of E. And E, this E over here is the elastic energy stored in just one of the springs. So to do that, what we're going to have to do is we're going to have to treat this as one spring and get an expression for its elastic energy and see how it's related to the elastic energy stored in just one of those springs. So let's do that. Let's say that the elastic strain energy of the new system is equal to half multiplied by the force or the new force, which is 2F, multiplied by the new extension. We don't know what the new extension is. Let's say we're trying to work out this extension. So the new, let's say extension N for like the new spring. The extension of the new spring is equal to the force, the total force exerted on the new spring multiplied by the spring constant. I got this equation from Hooke's law, F equals Kx. Good. So the question now is, what is the total force acting on this new system? We're going to treat this system as one spring with spring constant, whatever a spring constant is. So the new force is 2F. The question now is, okay, what is the spring constant of this system? Well, you need to know the following rules. And that is, if you have springs in series, so I have 1 spring, 2 springs, 3 springs, and every spring has some spring constant. This is K1, this is K2, this is K3. Then the total spring constant could be given by the following relationship, which is 1 over the total spring constant is equal to 1 over the spring constant of your first spring plus 1 over the spring constant of your second spring. If you only had 2 springs, this would just be the equation. But if you have a third spring, then it'll be plus 1 over K3. If you had a 4th spring, 1 over K4, and so on and so forth. And this is for series, for springs in series. Now for springs in parallel, like the question given, then we're going to have to use the following relationship. And that is the total spring constant of this arrangement is equal to, let's say this had a spring constant of K1, this K2, K3 here. It will be K1 plus K2 plus K3. So it's just the sum of the individual spring constants. This is different, and in fact, this is the opposite to the resistor rules that you would have done in IGCSE. So remember, for resistors, if it was series, you just summed it, and if it was parallel, you did 1 over R equals 1 over R1 plus 1 over R2. So yeah, for spring constant, it's the opposite rule for resistors. So just make sure you don't confuse the two. So we have a parallel system. So I know the total spring constant is just going to be the sum of your springs. And this has a spring constant K, this has a spring constant K, and this one K. Why? Because it's the same spring. So your total spring constant is going to be K plus K plus K, which is just 3 times K. So this is the spring constant of this system. So we said the extension of this new system is the total force, which is 2F, divided by the total spring constant, which is 3K. And I know that the extension of the first one, of the first system, is just given by F over K. Because for the first spring, you're just applying a force of F, and it just extended by delta X, and the spring constant is just K. So what I can say is I could say, therefore, the extension of the new spring is equal to 2 over 3 multiplied by K, because this F over K is just equal to the extension of your first spring. Okay, so this is your, sorry, I'm very, very sorry. That should say 2/3 multiplied by extension. Because the extension of is equal to the force over the spring constant. So now that we have the extension, we could go back to this equation and we could say that the elastic strain energy, I'm running out of space, is equal to half multiplied by 2F multiplied by 2/3 by the extension. But what I'm going to do is I'm going to take out the 2 and take out the 2/3 to the outside. And you'll see why I'm doing that. So I could say the total elastic strain energy. Well, what is 2? What is 2 times 2/3? That's 4/3. So we could say it's 4/3 multiplied by a half F delta X. But we know that a half F delta X is equal to E, is equal to the energy stored, elastic strain energy stored on the first spring. So the energy stored on your new spring is 4/3 is equal to 4/3 E. And that is, what is that? That is option C. I hope I didn't waffle too much. All right, question 9. A proton and an electron have equal kinetic energies. The speed of the proton is V. The mass of the proton is 2,000 times greater than the mass of the electron. We could write that as a relationship. We could say that the mass of the proton is equal to 2,000 times the mass of the electron. Which of the following expressions gives the speed of the electron? And it wants the speed of the electron in terms of V. V is the speed of the proton. So it wants the speed of the electron in terms of the speed of the proton. Well, to do that, you're going to need an expression for the speed of the proton and an expression for the speed of the electron, and then compare the two so you could have one as an expression of the other. So let's first of all write down an expression for the speed of the proton. So the speed of the proton, which is just V, is equal to square root, and I'm using this equation, by the way. I'm using the equation kinetic energy is half mv squared, because the question involved speed and also it said they have the same kinetic energy. So I'm going to make V the subject. So the velocity of your proton is equal to square root 2 times the kinetic energy of your proton. And by the way, the kinetic energy of the proton is equal to the kinetic energy of your electron, right? And the reason that's the case because it says proton and electron have equal kinetic energy. So the velocity is square root 2 times the kinetic energy over the mass of your proton. Okay, so this is your expression for the velocity of the proton. Now let's get an expression for the velocity of the electron. So the velocity of the electron is equal to, just like before, square root 2 times the kinetic energy, which is the same as the kinetic energy of the proton, because they have the same kinetic energy, over the mass of the electron. Well, I'm going to put my mass of the electron in terms of the mass of a proton, because I am trying to get this on this equation. So I could have VE as a form of something multiplied by V, the velocity of the proton. Hope that made sense. So what I'm going to do is I'm going to use this relationship and say the mass of the electron is equal to the mass of the proton divided by 2,000, because we know the mass of the proton is 2,000 times larger. So I'm going to substitute this in. So mass of the proton over 2,000. And this is your velocity of the electron. But we're trying to just get square root 2 EK over MP. So we could substitute for V. We could put V in instead. So we could have VE in terms of V, because that's what we're trying to do. So we're going to have to do some maths. And the first rule I'm going to use is if you have like a three-way fraction such that you have A over B over C, where B over C is like in brackets, then what you do in this case is you say that this is the same as A times by C over B. So you took the C to the top. This is slightly different than if you had A over B as a bracket divided by C. If this was the case, then you take the C to the middle. So that's one way to think about it. Or you could just use a four-way fraction and say that this is technically 2 EK over 1, right? Because 2 over 1 is just 2, right? And over MP over 2000. And then the four-way fractions are really easy to solve. You just multiply the ones further apart and the ones closer apart. So this just becomes equals to 2ek multiplied by 2000 over MP. So yeah, however you want to simplify the fraction, but what I'm trying to do is I'm trying to make it into one fraction. It's never good to have like one, like a three-way fraction or a four-way fraction. So let's simplify and say that this is equal to square root 2000 multiplied by 2 times ek. So I took the 2000 to the top, divided by the mass of the proton. And what we can see is inside this third is 2 times ek over mp, which is, the expression for the velocity of the proton. So I'm going to use the third rules now, which is square root a multiplied by square root b is equal to square root a times b. I'm going to use this rule to simplify this to square root 2000. So I split it into square root 2000. That's basically your a, and your b is a square root 2ek over mp. Okay, so this is your velocity of the electron. But what I can say is I could say that square root 2ek over mp is the same as v. So this we could simplify to say velocity of the electron is square root 2000 multiplied by v, because this is equal to v. And the option is A. Question 10, an electric pump has an output power of 25 kilowatts and an efficiency of 52%. Which of the following expressions gives the rate in kilowatts at which energy is dissipated? Well, it wants the rate in kilowatts, so I'm going to ignore the kilo because the answer is in kilowatts. And then I'm going to try to understand what is energy dissipated, because that's what it's asking for. Well, energy dissipated is the same thing as your energy lost or transferred to the surroundings or wasted energy. That's what energy dissipated means. So it wants the power of your energy lost. So you should know that, and it's giving us efficiency. You should know if something's 52% efficient, that means 52% is useful and 48% is wasted. This wasted is your energy dissipated. So that's what we're going to focus on. So we're going to say that the energy dissipated is equal to the total energy, let's say T for total, multiplied by 0.48. So multiplied by 48%. So this is just basically saying 48% of the total energy, which is the energy dissipated. Well, to do this, we're going to need the total energy. So how do we work out the total energy? Well, it's given us efficiency and it's given us the output power. In this case, this output power could be considered the useful power, because that's what you're able to get out of your electric pump. So what we could say is useful power over total power is equal to efficiency. And useful is 25 kilowatts. So 25 kilowatts over the total is equal to 0.52. That's the efficiency. We want the total, so we could swap these two around. So we could say that the total is equal to 25 kilowatts over 0.52. Now we're going to sub this in for this total here. So we could say that the energy dissipated is the total, which is 25 kilowatts over 0.52, multiplied by 0.48. Now, which of the following gives this as the option? That would be C. So 0.48 times by 25 over 0.52. Well, it says give your answer in kilowatts. That's why they've removed the kilowatts from the answer. Right, question 11. The engine of a motor boat provides a constant horizontal force. As the velocity of the boat increases, the resultant horizontal force on the boat decreases. Well, that makes sense, because the faster your boat, the more frictional and drag forces, and those are opposing your forward force, so the total resultant force will decrease. Eventually, the boat will travel at its terminal velocity. This is the case when your forward forces is equal to your, backwards or your frictional forces. Okay, the constant horizontal force from the engine is 5,500 newtons. So this is the forward force. State what is meant by a resultant force. We're going to say that the resultant force is the sum of all the forces acting on an object. So if you sum up every single force on an object, this will give you the total resultant force. Okay, at a certain time, the drag force was 3,100 newtons. Calculate the acceleration of the boat at this time, and it's given us the mass. So once acceleration is given us mass, so of course we're going to say from Newton's second law, F is equal to mass times acceleration, where F is the resultant force. Always remember that this force in Newton's second law is the resultant force. So we could say that acceleration is the resultant force over the mass. Well, what is the resultant force? I know I have a forward force of 5,500 and a backwards force of 3,100. So the resultant force is just going to equal to 5,500 minus 3,100. And now you have to divide by the mass, and the mass is 7.5 times 10 to the 3 kilograms. So let me put that my calculator. This gives me 0.32. So I'm going to say 0.32 meters per second squared, because that's the unit for acceleration. Okay, the terminal velocity of the boat is 4.8 meters per second. When does the boat reach terminal velocity? It reaches terminal velocity when the forward force, which is 5,500, is equal to the frictional force, which is 5,500. Calculate the output power of the engine. Well, we know that power is energy over time. In this case, the energy transferred, the energy is the energy transferred to the boat. Well, what energy is transferred to the boat to allow it to reach terminal velocity? Well, it's just the work done on the boat. So we know that work done is energy transferred, and we know that work done is force times distance. And then you should also know that distance over time is the same as velocity, the terminal velocity that would be. So the power is equal to force times the terminal velocity. This is just the equation people tend to memorize anyway. So it will give you, well, what is the force? The force you have to apply to reach the terminal velocity is 5,500 newtons, and the terminal velocity is 4.8. So let's do that. You get, if I put it to two significant figures, but I'm going to put it to 3, 2.64 times 10. 1, 2, 3, 4. Times 10 to the 4 watts. You're probably thinking, shouldn't have you used two significant figures? I agree, you probably should have, but I know like I won't drop a mark for 3 significant figures. And the answer was like 26400. It just, it was too good to be true to just say 2.6. So yeah, I technically broken the physics rule. You know what? Let me not break it and just write 2.6 times 10 to the 4 watts. All right. Yes, your syllabus is quite confusing in terms of significant figures, but generally always use the lowest number given in the question. It's just sometimes when you look at the mark scheme, it gives you not the lowest for some reason. But yeah, it's a rule that you can just always use, and hopefully you'll get the marks. A student carried out, oh, by the way, if you're not sure, like this is just so confused, just write the full answer first, so 26400, and then put the significant figures at the end. So even if this is not the right number of significant figures, they saw the correct answer on your working out. So you definitely should get a mark. Question 12, a student carried out an experiment to determine the Young's modulus of Constantan. The student had a Constantan wire with cross-sectional area. Given the unstretched length was 4 meters, the student had enough slotted masses to apply a weight of up to 150 newtons to the wire. The break-in stress of Constantan is about 420 megapascals. Deduce whether the wire could support a weight of 150 newtons. So you're trying to say, when you're trying to find out that when you apply a force of 150 newtons, would the break-in stress be above or below? If it's above, it'll break. So would the stress be above or below? If the stress is above, it's going to break. If it's below, then you're fine. So how do we work out the stress? We know that stress is force over area. And we know the force, we're trying to see if this force will break it. So we're going to plug in 150 as the force. And the area is 3.97 times 10 to the minus 7. Let me quickly put that on my calculator. So I get 3.78 times 10. 1, 2, 3, 4, 6, times 10 to the 8 pascals, because that's the unit for stress. The breaking stress is 420 megapascals, or you could say 4.2 times 10 to the 6 plus 10 to the 2. So times 10 to the 8 pascals. So what I can conclude is I could conclude that 3.78 is less than 4.2. Thus, it won't break. I think those are very generous 3 marks. The student added slotted masses to the wire and determined the corresponding extensions. The student plotted a graph of force against extension. So a force against extension graph, the first thing that should come to mind is that the gradient represents force over extension. So that's what the gradient is. And that is, of course, the spring constant. Also, that what should be coming to mind in case needed is the area under the graph is force multiplied by extension divided by 2, because it's the area of a triangle. And that's equal to the work done, or the elastic strain energy stored in the spring. So let's see, what are we going to have to do for this question? Show that the stiffness of the wire is 1.3. Stiffness is the same as spring constant K. So we want to work out the gradient. So let's pick some points. I'm going to pick, this looks like a good point. Maybe this looks like a good point. So I picked these 2 points. You could pick whatever 2 points. Just make sure that you use at least like 50-60% of your straight line region. So you don't want to make a triangle like this. This is not 50% of your straight line region. So it's not going to be accurate enough, and the mark scheme might not accept the answer either. So yeah, draw your triangle to work out the gradient. Mark the point. So this is going to be, this is 40, 60, so 50, 52, 54. So this is 54 newtons. And then this, with this 15, 10, sorry, so 10, 12, so this is 12. So your y-axis has, or the height of your triangle is 54 minus 12, which is 42. And then your x-axis, well, this is going to be 4.2. And this is 1. So 4.2 minus 1 is 3.2. So, and keep in mind, this is 3.2 millimeters. And it says show that the stiffness is newtons per meter. So obviously you want the extension in meters. So let's say the gradient is 42 newtons divided by 3.2 times 10 to the minus 3. Because to go from millimeters to meters, you have to divide by 1,000. And let's check what we get. So we get 13125 newtons per meter, which obviously is around 1.3 to 2 significant figures. Okay, the relationship between the stiffness of the wire and the Young's modulus is given by this expression, where K is the unstretched length of the wire and A is the cross-sectional area of the wire. Determine a value for the Young's modulus of Constantine using the student's data. Might be a good exercise, by the way, to derive this expression using Young's modulus, which is stress over strain, because some questions do ask you to arrive at a similar sort of expression. But anyway, we have to use this expression to work out the Young's modulus, which is E. So let's first of all rearrange the equation. So we could say E is equal to Kx. I took the x to the other side, and then I divided by A. So Kx over the area. We know what the spring constant is. K is, let's say 1.3125 times 10 to the 4. Never use rounded values until the very end. multiplied by x. X is just the unstretched length, which I believe was given previously as 4 meters. So multiplied by 4, divided by the cross-sectional area of the wire. That was also given as a student cross-sectional area. 3.97 times 10 to the minus 7. So over 3.97 times 10 to the minus 7. That will give you your Young's modulus. Let me see what we get. Yeah, I get 3.3 times 10. Sorry, I made a mistake. Yeah, I forgot to multiply by 4. So I get 1.3 times 10 to the 11. Pascals, because Pascals is also the unit for Young's modulus, or you could say Newton per meter squared. Good, so this will be my answer to 2 significant figures.